Hi, I'm Dr. Greg Graves, and today we are moving into the final phase of the systems decision process, solution implementation. Here's where we are in the course. We're in the final block containing instruction. We'll spend 2 lessons on this phase, and then you will finish up with your project presentations. After today's lesson, you should be able to list and describe the tasks included in the solution implementation phase of the SDP, describe the importance of testing and evaluation for systems engineering, understand ethical considerations in project implementation, develop a work breakdown structure for a project, and develop a linear responsibility chart for a project. As you know, the solution implementation phase is the 4th and final phase of the SDP. It is represented by the blue circle in the SDP diagram because now that we have a decision, we're aiming for blue skies and smooth sailing in order to implement the chosen solution. The input to this phase is the solution decision produced by the decision-making phase. In order to determine how to translate the decision into action, we have 3 tasks that comprise this phase. First, planning for action involves determining the people, tasks, resources, schedule, processes, and interactions that are all aspects of the project that implementing the solution is equivalent to. Once a good plan is developed, we execute the plan and put it into action. And finally, during the execution, monitoring and controlling key elements of the project, including cost, schedule, and performance, among others, allows the project management team to take preventive actions to avoid events that would adversely impact successful implementation. The output of the solution implementation phase is additional needs, which may be in the form of new systems that are needed, new decisions that are required, or perhaps new processes that are needed to implement the solution. These additional needs serve as the starting point for new iterations of the SDP in order to come up with solutions to meet them. We'll be looking at several key concepts in this block, including the work breakdown structure, which we're discussing today, performance measurement, and then the monitor, assess, control cycle that we'll cover in Lesson 17. If you recall, way back on Lesson 1, we talked about the 3 fundamental tasks of a systems engineer. The first task involves using systems thinking and considering the complete problem throughout the system life cycle. The second task involves being able to understand customer needs and translate them into functions, requirements, and performance measures for a solution. The third task shows where a system engineer will be required to step up and lead the design team: requirements analysis, design synthesis, and system validation, so that the solution system is successfully realized or implemented. So you see, the solution implementation phase is primarily related to fundamental task 3 for systems engineers. Additionally, you should note that system validation is a primary concern for systems engineers. You'll recall that we talked about system validation when we looked at the systems engineering V in our discussion of design methods back in the solution design phase. It sits up here at the top right of the diagram and represents the final determination that the system actually does what the customer was looking for in the solution. Testing and evaluation is how we accomplish that system validation. But that's not the only time we do it. We should actually be doing it throughout the systems engineering process, particularly along the right side of the V. We do testing and evaluation on components before we combine them into subsystems. We do it on subsystems before we combine them into the final system. And then we do testing on the system itself to ensure that it meets the design requirements we determined for it. All along, we are using the concepts of value and the ability to measure performance in testing, concepts which you've seen throughout your study of the SDP. As an example of how testing and evaluation is done in practice, take the example of the turbofan engine found on most commercial airline aircraft. These engines are designed for efficiency during flight, most of which will be at high speed at cruising altitude. These diagrams show the engine's cross-section and the intended airflow patterns. Well, there are regulations in place that provide additional requirements for successful operation in various conditions, one of which is bird ingestion. The engine must be able to operate successfully even if a bird gets sucked into it. There's required testing and evaluation. There are testing facilities where they shoot bird carcasses into running engines and evaluate how the performance of the engine is infected. There were recommended changes to the regulations about 10 years ago based on U.S. Airways Flight 1549. Here's a short video that shows different tests for a typical turbofan engine.
Before the engine could be certified for flight, it had to be put through a battery of demanding tests.
The testing is to assure that the engine can fly in any environment safely. We look at any extreme environments and make the testing more severe than what you'll see in operation on an aircraft. We have water ingestion testing. We take in about 4.5 tons of water a minute and show that the engine can continue to operate and not stall, taking in that kind of volume of water. We also do hail ingestion testing. We have several little cannons that shoot hail into the engine. They shoot about 3/4 of a ton of hail in 30 seconds.
Nothing was left to chance. Technicians tried to recreate and analyze every possible problem that could happen to the engine.
An engine, when it's operating on an aircraft, takes in a lot of air. It can also take in anything else in the environment, such as a bird. So we're required per the FAA to shoot bird carcasses into the engine and to show that we can continue to sustain operation even after taking in the bird carcasses.
So what was it about U.S. Airways Flight 1549 that drove changes to the regulations? This flight was the miracle on the Hudson. You may have seen the movie Sully with Tom Hanks that focused on the behavior of the pilots and the investigation. What led to the need for their heroic action was that at least 2 Canada geese were ingested in each of the engines, and it damaged the core, not the fan blades. So all thrust was lost, and they were forced to ditch in the Hudson River. Fortunately, all passengers and crew survived. 2 things contributed to the need for new testing regulations. First, it was evident that the engine technology had evolved since the original rules for testing were written. Second, the original tests focused on takeoff conditions when the aircraft is on the ground, because that was where bird strikes were anticipated. The incident on this flight happened during the climb after takeoff, and the aircraft was already in flight, so there was no option to abort takeoff. So the new rules added testing under in-flight conditions that would exist during takeoff or landing, and they concentrated on the engine core instead of just the fan. This example shows how previously established testing or requirements sometimes need to be updated based on changing design, such as the evolution of the engines, or new information, such as the altitude of the bird strikes. This concludes the first video for today's lesson. We'll get into the planning task in the next video.